All right, so let me begin a little bit by recalling what we did last time, just to kind of refresh your memory. So the one topic we talked about was just linear maps in a Banach space and hyperbolicity so we had A mapping from a Banach space into itself, and we had the decomposition into stable and unstable subspaces. And you're expanding in the unstable direction and contracting in the unstable. Sorry, the other way around. So there were uniform rates of contraction and expansion. So then we kind of looked at a slightly more nonlinear version of this, which was taking Lipschitz perturbations so we took a map F, which was capital A plus little f. So F is L Lipschitz. And if this Lipschitz constant was small enough, we said that there existed unstable and a stable manifold. So we had the unstable manifold and the stable manifold. Maybe one remark I should add, since people asked after the talk, it's not so difficult to prove that these objects exist. It's not more difficult than, for example, proving the inverse function theorem or the implicit function theorem. What is a little bit harder is to actually prove that they're as regular as f. So the harder part is the property that they are as smooth as the perturbation. So, for example, if you have a smooth perturbation, then the manifold itself is smooth, and that requires a little bit of work. So maybe I'll say, if you're familiar with the existence theory of ODEs, usually you can always prove existence, but losing one derivative and recovering the last derivative is kind of a notoriously tricky point in, about ODEs. Okay, so then after we looked at this setting of a single linear map, but in a Banach space, we talked about cocycles. So this meant a vector bundle, so X, a compact metric space, and F was some dynamical system, so continuous, maybe even Lipschitz. And we had a vector bundle E over X and map, say FE, covering the map over X. And so once we have these vector bundles, we can talk about hyperbolicity for them. So we discussed hyperbolicity of cocycles. So in other words, we had the decomposition into invariant subbundles plus uniform contraction and expansion. And just as a reminder, our interest is mainly in studying these objects on manifolds, but inside of these manifolds, you can end up having to work with other submanifolds or other metric spaces, some kind of odd fractals that could live inside. So that's why we're working with a base which is a general compact metric space. OK, so we talked about this, and I then talked about this notion of quasi-hyperbolicity. Which I stated as the following theorem. So for a cocycle E as above. So I think maybe people were a little bit confused. I'll always assume that if I have a vector bundle, there's some kind of dynamical system underlying it. So I think there's an objection to the notation that I was calling the vector bundle the cocycle, but there's always some map implicit. So we have the following equivalent properties. So the first one looks kind of simple-minded. So for any vector, any non-zero vector, in your vector bundle, if you look at the set at the orbit of this vector over all, so both in the future and in the past, this is unbounded. The second property was that there exists a hyperbolic cocycle E prime and an equivariant embedding E into E prime. So it's clear that if you have such an embedding, then every vector has to grow exponentially either into the future or into the past, and most vectors will grow in both directions if they're not contained in the subspaces. And the third was a characterization in terms of kind of a functional analysis, which was that if we considered Fe acting on continuous sections on the Banach space, so we view C0 of E as a Banach space with C0 norm, then Fe has no kernel and closed range. So it's an isomorphism onto some proper subspace. And one thing that I emphasized also last time was that almost everything that we do is completely independent of norms as long as the norms are equivalent. In other words, as long as there's a constant such that the norms are comparable up to that constant. So here, the C0 norm on the Banach space of continuous sections, for example, is there's an implicit norm on the cocycle E, but if you change that norm by something equivalent, the statements still hold. All right? Any questions? So I should say, I'm not going to prove this. There's some of these implications are easy, others are harder. So the hardest one is to go from this weakest property that if you just take any vector, you have some growth into the future or into the past, and somehow cook up this hyperbolic cocycle that you embed into. So this requires some work.
You said 1 minus Fe last time?
Oh, yes, I'm sorry. You're absolutely right. Yeah. Oops. Yes, I apologize about this. Yeah, so 1 minus Fe. Because Fe is an isomorphism, yes. And the point was that being hyperbolic meant that 1 minus Fe was invertible. Yeah, so I apologize. Okay, any other questions?
Does all of that imply that if I say start by e to the I theta 1 minus Fe, then that also is no kernel, etc.?
Yeah, so if you can complexify it, yes, I think that should also be true. Yeah. OK, so the reason for the interest in this notion was that, so I should have also recalled that we said that if M is a manifold and we have F from M into itself a diffeomorphism, then we said F is Anosov if df, the derivative acting on the tangent bundle, is hyperbolic. So if we have S inside M, a F invariant submanifold, then if I take the tangent bundle of S, so if I have F restricted to S, and I take df, so it acts on Ts, then this is quasi-hyperbolic. In other words, if you have your sort of stable and unstable foliation, then this invariant submanifold S, there's a priori no reason for it to be nicely, I mean, it could be transverse to this foliation, for example. And at least in some parts of the space, it will have to have some parts of the manifold where you have actually some better compatibility. So I should say that, you know, there will be some parts of the manifold where you will have an honest decomposition that will be into stable and unstable subspaces, but there could be other large parts where it's not. So this is the kind of object we'll be interested in. But there's also an important dual notion, which is good to kind of keep track of, and also occurs quite a lot. So dually, there's a notion of, the terminology is unfortunately not dual, so there's not really a good terminology. Somehow I think these two notions appeared independently, and then people said, oh, look, they're similar. So this is called linear transversality. So if I have a E over X, a cocycle, let me define, so this is a definition, so I'm going to define ES to be those vectors E and some EX independently of, you know, so for each point I take the fiber and I ask the following question about the vector. Is it true that if I take its forward orbit, this goes to 0 as n goes to plus infinity? And similarly, EU such that it goes to 0, but now n going to minus infinity. So the theorem, the dual notion, is that the following are equivalent for a cocycle E over X. So the first one is that if I take ES plus EU, and so for any x, this surjects onto E of X. I'll give you an example in a moment. The other one is that there exists a hyperbolic E prime and an equivariant surjection E prime onto E. And the third one is that the dual cocycle is quasi-hyperbolic. So let me just recall here that what is the dual cocycle? E star, well, the fiber is just the dual vector space, and the map well, what do? You have x, you have f of x, you have e of x, you have f of x. So here you have fe of x. So then on the dual spaces, you have a map that goes the other way. This is e dual of f of x. So this is fe transpose of x, and then e dual of x. So you have to take f e star to be at the point x to be fe transpose of x inverse. So if you have a matrix, you just basically take the transpose inverse matrix. And that gives you another cocycle, the dual cocycle. And so I should have said, so cocycles that satisfy any of these equivalent conditions are called quasi-hyperbolic. Cocycles that satisfy any of these equivalent conditions are called linearly transverse, and they're clearly dual to each other. Okay. I should say, so you can see that this condition, so if you have, where is it? If you embed into a hyperbolic cocycle, when you dualize that, you get a surjection onto the duals. So the dual of a hyperbolic cocycle is hyperbolic, but when you dualize that embedding, you get instead a surjection like this. Okay. So okay, so I'm not going to prove this either, but I want to give you an example. In fact, it's an example that you've probably seen if you've learned Moore's theory from Milner's book. So, and I should also say, this is the kind of example where, I think Arnauld says if you give a definition, first thing you should do is not to give an example of something that satisfies it, but of something that does not satisfy it. So I want to give you an example of a cocycle which is not linearly transverse. So if you take the torus, so you have the gradient flow of the height function on T2, embedded like this. So if you, one thing I was kind of cheating a little bit about is I took discrete time dynamical systems, and now I'm saying take the gradient flow, which is a continuous time dynamical system. So if you don't like that, you can just take the time one map of this gradient flow. All right. So there will be 4 fixed points, which are over here, that I drew over here. And what is the dynamics? So this point is repelling. So the stable subspace at this point is, this is an unstable fixed point. So if I look at these two things, then the whole tangent space is EU, right? So every vector decays, but if you have to run the flow backwards. The same thing happens over here, so except that dually, so you have to, everything contracts into the future, and these points are hyperbolic fixed points. Actually. So over here you have hyperbolicity, so let me do the colors correctly. So these will be expanding, and over here again, you're kind of going down, but So these 2 points are saddles. They have an expanding direction and a contracting direction. But what is interesting about this picture is that there's something highly non-generic that's happening. In other words, if you look at this unstable manifold, this red trajectory, it hits this point. And that is a non-generic behavior, because if you perturb this a little bit, you will end up, you should end up actually, this trajectory should really have landed at this bottom point. So this trajectory, so this behavior is non-generic. If you perturb it, the picture, the flow lines become topologically non-equivalent. And I'll state the relevant theorem in a moment. But you can see that this point, so if you take a direction here, so you see that a tangent vector that's along the flow line, it gets contracted both into the future and into the past. So this is, so you have here that ES is equal to EU at this point, and it's one-dimensional. And every other vector which is not tangent to this flow line, it gets expanded both into the future and into the past. Okay? So this is an example of a cocycle which is not linearly transverse. So this is not linearly transverse. The flow lines change under a small perturbation. So topologically, they're not going to be conjugate. And the reason why people initially were interested in this notion of linear transversality was the following theorem, due to, I guess, many people, so in different kind of increasing order of generality. So Pallas, Smale, Robbins, and I think the last the person who proved the final piece is Robinson. So the theorem is that, so if you have f from M into itself a diffeomorphism, if it is, so I'll remind you the definition in a moment, but you've seen it already in Daniel's lectures. I don't know if you see it, but you've seen this definition earlier, but I'll remind you in a moment. So if it is axiom A and linearly transverse, so and Tm is transverse, then F is C1 structurally stable, which means a C1 perturbation is topologically conjugate to F. So in other words, if I perturb a little bit the diffeomorphism, there's a homeomorphism from the manifold into itself, which takes the orbits of F to the orbits of the perturbation. Okay. So if you remember last time, I said that Anosov diffeomorphisms are structurally stable because they, so that's kind of a classic fact that you can try to prove. It's not too bad with the tools that we already have. And if you have these Morse gradient flows, as long as they satisfy some kind of transversality condition, they're also structurally stable. So if you perturb that, you know that if you perturb a Morse function, it becomes generic in some appropriate sense, and then any perturbation of a generic one will be topologically at least conjugate to the original one. Okay, so the moral is that the first picture you will draw will actually oftentimes not be generic. So this is kind of, what happens if you tilt a little bit the torus, the gradient flow for that looks different from the original one. Okay. Let's see. Any questions about any of this?
Can you repeat the explanation as to why this isn't linear complete transverse?
Yeah, so in order to be linearly transverse, you need the stable and unstable space to span your ambient thing. And if I take this point and I look at its tangent space, I claim that, so look at the vector that's tangent to this line. Then such a vector is contracted both into the future and into the past. So this means that it belongs to both ES and to EU. If I take any vector that's not tangent, it will grow both into the future and into the past. So this means that ES is equal to EU and is this one-dimensional space. And it does not have the property that ES plus EU. So ES, I don't mean here that it's a direct sum. I just mean that they span. Yeah. Okay?
Thanks.
Mm-hmm. Any other questions? All right. So now I want to move on to geodesic flows and just remind you a few things about those. Sorry. Yeah. Oops. Can you still hear me? Yeah. Okay. Oops. I want to be careful not to press anything. So, okay, success. I think it's good. Yeah, you can hear me. Yeah, good. All right. All right. So I'll begin with just a few reminders on geodesic flows in general, and then I'll specialize to the case when the curvature of the manifold is negative, and then we'll see that in that case we get hyperbolic flows. Depending on how much time I have at the end, I'll talk a little bit about kind of the symplectic geometry picture of associated to geodesic flows. So now M is going to be a Riemannian manifold. The basic object we'll be interested in is the tangent bundle. And the thing that becomes a little confusing is that we're going to be also looking at the tangent bundle to the tangent bundle. So if we have M, and we have Tm, and so if I have a point here, a little x, and a vector v, so this is x and v, then I can talk about the tangent bundle at the tangent space at xv to Tm. And so I have this projection map. So of course I can project onto the tangent fiber here, so I can always project down. And I have a kernel, and the kernel is actually, again, the same space, because the whole fiber, this is a vector space, and it's the tangent to a vector space, the tangent bundle to a vector space is trivial and is that vector space. So we have, again, this structure. So this didn't need to have a Riemannian manifold. I'm going to call this part, I'm going to call this, so I'm going to define this to be the vertical part of the tangent bundle of Tm. So we have this direction here, vertically. And what we'll see, so the one geometric interpretation of the Levi-Civita connection is that it gives you a horizontal, a lift, a way to say that a vector on the base, I can lift it to a vector, a tangent vector up there. So we have the Levi-Civita connection. So in differential geometric terms, is just a way to differentiate sections of the tangent bundle, and it's valued in one forms with coefficients again. And in vector fields, so actually, some of the constructions I'm going to make, they work with any, as long as you have some connection. It doesn't have to be the Levi-Civita connection. It's just that the Levi-Civita connection, it determines the geodesics, not some other kinds of class of curves. So I recall that gamma from a map from I into M, so I inside R is an interval. So we say that it is a geodesic. Well, one definition is that it minimizes distances locally, but if you try to write down the variational equation, that imposes some ODE on this map, and the condition is that if I differentiate so I have a curve, it has a vector field, has a tangent vector field along it, and I just want this to be parallel. Right, so this is the definition of a geodesic. Again, if you have any connection, this leads to a notion of geodesics for that connection. Okay, so I define now the horizontal subspace. So T horizontal at xv of Tm is defined by the condition that if I have gamma, again, for my interval into now Tm is horizontal. In other words, it's tangent to this horizontal distribution. So I want to define a family of horizontal subspaces here if, again, if I differentiate, but now I take gamma of T, and then I take pi of gamma dot of T, or d pi, then this is equal to 0. So what does this mean? You see, gamma, if I have a curve in the tangent bundle, I can of course project it and I have a curve on M, but the extra data is that at each point of my curve I have not just a point on M, but also a tangent vector above it. Right? So this is the same as such a map. And I'm saying that if I take this vector, this family of vectors that I have, gamma of T, that depend on they live on my curve, if I differentiate them along the vector field tangent to the curve, then I get 0. Okay? This is a definition. And now I have, the tangent space now to Tm decomposes as the horizontal part plus the vertical part and I can write down, for example, the geodesic vector field so we'll call this x at the point xv. With respect to this decomposition is just v plus 0. So this is a vector field. In other words, at each point of my manifold is Tm, I have a tangent vector, and I just take, well, I have v. So I'm sitting at the tangent vector, and I just put that tangent vector, but I orient it horizontally. So again, kind of the picture is that, so this is m, Tm. And so if I'm sitting at this vector v, I know I have a way to point horizontally. So now this is a vector field, and essentially from the definitions, it gives you a flow on Tm, and this flow is going to be the geodesic flow. So the flow of this vector field is the geodesic flow. Let me call it GT. And the question we want to understand is what is the derivative of GT. So in other words, I have this flow, I have this decomposition, and I want to know how does this flow act with respect to this decomposition. Of course, crucially, it is not going to be an invariant decomposition. So if I have now a manifold with two subbundles of the tangent bundle and a flow on that manifold, so then I flow, and then I want to know how these tangent directions move. Okay? And the answer is given by the theory of Jacobi fields. So let me remind you. So if I have gamma a geodesic, then a vector field along this, j from I into, let me call this gamma pullback of Tm. So now I have my manifold M, and I have my geodesic gamma, and now I have some vector field j along gamma, and we say that j is a Jacobi field if we have the following equation. So I'll explain in a moment. So dot just means derivatives, and there's only basically one thing you can differentiate with, which is the tangent vector field along this geodesic. All right. So you see, and R is the curvature tensor. So as a reminder, the curvature tensor, if you feed two vectors into it, it becomes a transformation of your tangent space. So if you feed a third vector, you get back a vector. So that's what this ODE is supposed to be about. And you should think of this as some kind of matrix version of just the usual ODE x dot plus x double dot plus ax equals 0, where you see this ODE in particular is linear in J. So this these terms, they kind of determine some coefficients, but the curvature tensor is linear here, and of course it's linear in the second derivatives. Okay. Yeah?
In the geodesic vector field, so I'm a bit confused about the fact that V may not be in the horizontal distribution, so it seems to me there has to be
So let me explain the notation. So x is a point on the manifold, and v is a tangent vector at x. Right? So v is a tangent vector at x, and the horizontal subspace is naturally identified with the tangent space. So there's a natural identification that comes from this connection with txv, txm, and v lives here.
Right. Okay.
So that's why I put it here. Okay. Yeah, this is very confusing, so it's okay to...
I don't understand, so are you building J from gamma? When you say gamma, if gamma is a geodesic, then J is... And if so, then what is the formula for J?
So this is a definition, this is a property of a vector field. So if I have a vector field, so given a geodesic, so given then a vector field J is called the Jacobi field if it has this property. Okay? So there's many Jacobi fields. So so Jacobi field is determined by the value, let's say, at 0, and its first derivative at 0, so it's a second order ODE. And the proposition is that dgt, if I apply it to x and y, so let's say x plus y belong to tangent x v of Tm. So this is the horizontal and vertical components. Then this is, now I have to give you some vectors at gt applied to this thing. So this is going to be j of t, j dot of t, where j of t is the Jacobi field along the geodesic determined by xv with j of 0 equals x and j dot of 0 equals y. Okay? So given the time, I'm going to just maybe say a few words here, and then I do want to prove to you that negatively curved manifolds have Anosov flows and geodesic flows. And in order to actually finish it today, I'll kind of reduce to something which I think should hopefully be believable. But let me just say one thing about this theorem. What are we really kind of measuring here? So we have our x, the point, and the direction v. And there's two things you can move, two degrees of freedom. You can move x when you're in Tm. You can move in the x direction, or you can move the tangent vector, right? And making any of those motions generates a new geodesic. So I could kind of have this x prime and v prime. So I've moved in the x direction, but I've moved also the vector a little bit. And there's some associated geodesic to that point. And essentially, the way the equation of Jacobi fields arises is that you're interested in one-parameter families of geodesics. So if you have a map from a rectangle into your manifold such that the vertical lines are geodesics, then normal to those vertical lines, you exactly get these Jacobi fields if you differentiate. So, and essentially, it's just a matter of kind of untangling the definitions to check that this is the property that you want. So I want to consider the following situation. So, as I said, what I want to prove is that negatively curved manifolds have Anosov geodesic flow and to do this, so we consider the following situation. And again, it will be a matter of just following through the definitions to see that what I will prove now implies what I said about this flows, geodesic flows and negatively curved manifolds. So we have suppose E is a vector space plus a metric, so plus a Euclidean metric. So you can think of just Rn. And suppose I have a map R, so from my interval into symmetric maps of E, which simply means that AEF equals EAF. So suppose I'm given such a thing. So we consider the associated Jacobi equation, which is, again, just an equation for vector fields. So J from I into E is just a family of vectors parameterized by time. Okay, so this is the situation we are in. So of course, if we're in the scalar situation, if R is negative, then the solutions are exponentials, right? So if E is a one-dimensional vector space, then we have exponentials. And we would like to understand what happens in general. So if this is a matrix equation, so this is also called the Jacobi equation. So maybe let me see if people are following. So what is the initial data for such an ODE? So what do you have to specify to uniquely determine a solution for such a thing? Exactly. So you need to specify J of 0 and J dot of 0. And so we can rewrite this as a first order system. So if I have J and J dot, now if I differentiate these, then now I have a matrix. So I have 0, 1 applied to J and J dot. This is simply saying that J dot is, well, J dot, whereas here I have J double dot is by definition minus R applied to J. So now I have a first order ODE, but with twice the number of components. So this is on E plus E. And just to remind you, so one of them is the horizontal and the other one is the vertical copy of E. And what I want to show is that under some conditions, you have this expansion and contraction property. So our goal we're going to show the ODE contracts and expands a cone of subspaces in E plus E under, so assuming negative bound, negative sign of E, or of R. Okay. So what we want to show is that there's some cone of n-dimensional subspaces, which if I flow under this ODE, then this cone gets contracted. Okay? And then by what we talked about last time, this will imply this hyperbolicity of the associated flow and then of the Anosov flow. So the first thing to do is that, so we identify n-dimensional subspaces let me call them L inside E plus E that project surjectively on first factor with maps. So I'm going to call them phi L from E to E, such that the subspace is given by E plus FL of E for any E and E. So for example, if I have such a subspace L, I identify it with a map from the graph of a map from E to E. Okay? So I'm going to restrict for reasons that are quite reasonable if you kind of untangle this relation with the geodesic flow. We restrict to FL that are symmetric. So again, symmetric simply means that it has this property for the inner product. And so remember, we have an ODE for that acts on this vector space E plus E. So now I want to see how this ODE act on these subspaces, right? So there should be some ODE for these maps, phi L. So what ODE does phi L satisfy? So if I take E and phi L of E and I dot it, right, by the, so I fix an E and then I let things move, then on the one hand, this is.
So where is the time parameter? What's depending on the time? R, you varying R is L sub E. Where is the time parameter?
So everything except 1.
R depends on T.
R depends on T.
And E depends on T, but phi L is fixed?
No, phi L also depends on T. So this is on the one hand, and on the other hand, it's equal to E dot and then phi L dot of E plus phi L E dot. Right, so then this becomes 0, 1. Or, I mean, just write it. This becomes E and then, sorry, this becomes phi L of E, and then minus R times E. So then we get that phi L dot of E plus, now I can substitute, because these things are equal, E dot is equal to phi L of E. I get phi L composed with phi L of E. This is equal to minus R times E. So this was for any E. And so I conclude that phi L dot plus phi L squared plus R is equal to 0. And this kind of equation, so remember now phi L is a matrix, not a vector, so I can square it. So this is called the Rigidity equation. There's one thing I don't remember, is double C or double T for Rigidity? Double C. This is a Rigidity equation. And one thing to maybe remind you is that once you have these quadratic terms, of course, such equations can blow up in finite time, which corresponds to that space L becoming at some point having some pieces that are vertical. So those can blow up, so that can happen. But the proposition is the following. So I'm going to suppose, so now I have this tensor R, which depends on time, but I want to make an assumption on its signs. So for we have that the following property, that minus k1 squared EE plus REE So suppose I have such a property for my matrix R, which is the property that you will expect of your curvature tensor. Right? Actually, one apology, I'm going to make these inequalities strict, because I want things to be strict in a minute. And suppose phi L of t satisfies at t equals 0 the following inequality, that now if I take phi L of E, this is less than or equal to, sorry, again, strictly, K1 EE and greater than K0 EE. So in other words, the eigenvalues of the symmetric matrix are strictly between K0 and K1. So this is at time 0. Then it satisfies it for all t greater than or equal to 0. So the claim is, if my curvature tensor satisfies these bounds between K1 and K0, and my initial conditions also satisfy a similar kind of bound, then this bound actually is preserved for all times. And you can see that matrices which satisfy such a bound, they essentially form a cone, like what I was drawing there. And one thing you will notice that the more pinched your curvature is, so the closer K0 and K1 are, the thinner the cone is. So there's a special case of this proposition when K0 is equal to K1, and then you can just solve the ODE explicitly. This is the constant negative curvature case. So I have a question to the organizers. I generally really don't like going over time, but
you're not, because you started 5 minutes late.
Okay, so I'll just prove this theorem, which will take hopefully only 2 minutes. Okay, so okay. All right. So let me prove this proposition, because it's again, it's an important point. So so I'm going to let t0 be the smallest t for which, so I'm only going to prove one of these bounds, for which the largest eigenvalue of phi L is K1. So we're proving by contradiction so suppose that this upper bound at some point fails. Then there's a smallest time. The set of times when this largest eigenvalue is equal to K1 is a closed set. It's not 0. 0 is not there. And so there's a smallest time when this happens. Okay, when you have equality. And let E not be that eigenvector. Then what do we know? We know that this term phi L E plus R E E. What do we know? So this is, okay, so let me see if people are paying attention. So what is this? So E is the eigenvector of phi L of T naught with largest eigenvalue K1. Yeah, so we get K1 squared EE. And this term, by the assumption, this is greater than minus K1 squared EE. So this whole thing is, sorry? Is positive, yes. So this is greater than 0. Right. So from the Riccati equation, yes, E0, I'm sorry. Yes. Zeros. Yeah. So from the Riccati equation, we conclude that phi L dot E0, or let me call this with a minus, is, sorry, did I mess up the signs? So with a minus, it's equal to this. Yeah, so this is positive. Yeah, okay, good. Yeah. So phi L dot of E0 is negative. So this means that, so for epsilon sufficiently small, phi L, so this is a T0, phi L of T0 minus epsilon, E0, this is going to be greater than phi L of T0 E. So this function, phi L of T0 is decreasing, right? So it's decreasing, so it's larger to the left. But this is a contradiction to the fact that this was the first time that the largest eigenvalue reached K1. Okay? So this contradicts this property of T0 as the first time largest eigenvalue crossed K1. Because, right, we're saying that there's a vector which I apply this transformation, I get a quantity that's larger than what it was here when it was the maximum, right? And the lower bound is exactly the same, and this basically proves the proposition. Okay.
Questions?
And
No
claim
question.
now is that this verifies the cone condition?
Yes. So this verifies the cone condition, and because what we've shown is that if we start with this cone of vectors, of linear transformations, then it's mapped into itself. It's preserved. In fact, maybe I'll begin next time by maybe concluding some kind of exponential contraction things also with this kind of elementary ODE constructions.
Which cone? What's the cone?
The cone is, yeah. So the equation of the cone is it's linear transformations from E to E that satisfy this bound. So it's linear transformations for which the smallest eigenvalue is greater than k0 and the largest eigenvalue is less than k1. So these form a cone. Well, one has, they sweep out a cone in this E plus E, they're images. So the linear subspaces whose graphs so maybe let me say this way: there's a Grassmannian of all subspaces in E plus E, and that condition determines an open subset in that Grassmannian, which I'm looking at it in the chart Hom from E to E. So that's the open set which is mapped into itself by the dynamics.
More questions?
Can you remind how K1 and how these two Ks appear geometrically?
Yes, so thank you for that question. So remember, R was the curvature tensor, and if you have a sectional curvature, basically the sectional curvature is REE divided by EE, right? So that's more or less what the kind of quantities you're looking at. And if your sectional curvature, for example, is constant, then you could take K0 equal to K1, and you could actually solve this ODE explicitly, and then you would not have a cone. You could literally write down the stable and unstable subspace. If you know that your sectional curvature is, let's say, between -1 and -2, so it's variable negative curvature, then you could take K0 squared to be -1, and K1 squared to be -2. So these are the bounds on the curvature. Yeah.
So if n equals to 1, then it's nothing but a set of lines that slope in between K0 and K1.
Yes. Yeah, so it will be the lines with slope between K0 and K1, for example. Yeah, so that's a good maybe thing to keep in mind. Yeah, if you have the E is one-dimensional, that would be.
Okay, more questions? All right, I make one comment. Somebody who has taught this out more than once. It's nearly impossible to find a good exposition for it, so thank you very much.